to do is we're going to learn that there are certain things we can figure out without a calculator on the unit circle, which means we can figure out some trig values without a calculator. And as a result, they end up on the non-calculator part of your test and your exam. And so this paper, we split things up into different families. And the first family that we look at is the axes family. So we're worried about all of the points that are on the unit circle, but also touching either the x-axis or the y-axis. And the coordinates of these are really easy, because if the radius is 1, if you went 1 to the right, your coordinate would be 1, 0. If you went 1 up, 0, 1, here you'd have negative 1, 0, and 0, negative 1. And since those coordinates are so easy, it tells you you can do sine and cos of some angles really easily. For example, if I asked you, what is cos of 0 degrees? So first of all, in standard position, would you agree that 0 degrees would be right there? And if I said, what's cos of 0 degrees? The big idea says cos is always the x-coordinate on your unit circle, so cos of 0 degrees is equal to 1. You can verify that with your calculator. If you type in cos 0 and push enter, you will get 1. If I asked you what's cos of 90 degrees, well, in standard position, 90 degrees is right here. Cos is the x-coordinate, so cos of 90 degrees is 0. Cos of 180 degrees is negative 1. And cos of 270 degrees is 0 again. And with 0, we can also write 360 degrees, because they're coterminal, meaning they end at the same place. Now, those are our angles in degrees in standard position. We could change colors here and do them in radians as well. 0 is also 0, but 360 is 2 pi. Halfway around the circle, if all the way around the circle is 2 pi radians, does it make sense that halfway around the circle would be pi? And 90 degrees, which is half of 180, would be pi divided by 2. And 270 degrees will be 3 pi over 2. So now I could ask you the same question about sine. Sine of 3 pi over 2. You would say, okay, on my unit circle, 3 pi over 2 is here at the bottom. Here are my coordinates. And my big idea says that sine of theta is my y-coordinate. So sine of 3 pi over 2 is negative 1. And finally, we'll add tangent. First, if you did tangent of 0 degrees or tangent of 0 radians, tangent is sine divided by cos. And since sine is your y-coordinate and cos is your x-coordinate, you see that you would get 0 divided by 1. And 0 divided by 1 is 0. Same thing would happen over here at pi. Tan of pi would be sine, which is 0, divided by negative 1. It would also be 0. But when I go to the top here and do tan of pi over 2, well, now I would have 1 divided by 0. If I did sine is 1 and cos is 0, 1 divided by 0, but dividing by 0, that's not good. Not a good idea. So tan of pi over 2, if you type it into your calculator, it'll give you an error. We're just going to say it's undefined. Same thing happens down here at 3 pi over 2. We would say it's undefined because it's not possible. So this is the start. This is our axis family. It's the easiest family because the coordinates, you could just, because the radius is 1, they're super easy to find. All of your angles on the axis are easy to find in standard position because you know there's 360 degrees in a whole circle. You know that there's 2 pi radians in a whole circle. So we can figure out the axis family easily. Our next family that we're going to look at is the 45-degree family. What makes the 45-degree family is all of the reference angles are 45 degrees, or pi over 4. So if my reference angle, again, that's the angle back to the nearest x-axis. If this is 45, well, it's pretty obvious that that's 45 degrees. In quadrant 2, if I know my reference angle is 45 degrees, how do you figure out what the angle is in standard position? Remember? So if I wanted to find this angle here, I'll draw it in temporarily, and I know this is 45 degrees here, does it make sense that I could find this angle by taking 180 and subtracting the 45? So if I do that, I get 135 degrees. In quadrant 3, can you see that you would do the 180 and then add your reference angle of 45? That gives you 225 degrees. And in quadrant 4, you would go all the way around, which is 360, and minus your 45 degrees, you have 315 degrees. Now in radians, 45 degrees is pi divided by 4. Does it make sense that pi is halfway around? And if you did this is 4 equal sections, that one section would be pi divided by 4. 180 degrees divided by 4 is 45. So that's pi over 4, and I want to find this one. Okay? How did we find it in degrees? Right? You took 180 degrees and minus your reference angle of 45 degrees, and you got 135 degrees. In radians, we do the same math, we just think in a different unit. So if my reference angle is pi over 4 instead of 45 degrees, instead of doing 180, I would do pi minus my reference angle and figure out what that's equal to. But we have to remember some of our fraction stuff, because I have a fraction here. How do you subtract fractions? Common denominator. So can you see that you could change the pi to 4 pi over 4 to get a common denominator? And 4 pi over 4 minus 1 pi over 4 would be 3 pi over 4. And if you look at the pieces, it kind of makes sense that if this is pi over 4, that would be 2 pi over 4s. This makes 3 pi over 4s. All the way halfway is 4 pi over 4s, which is pi. Does it make sense that this one would be 5 pi over 4s? And then this would be 6 pi over 4s, and this one, pi over 4 is nicely because they're all equally cut. They're all the same size, so you can actually count them as you're going around to figure them out. But you could have also figured out the 7 pi over 4 by doing the same thing you would do in degrees. In degrees, you see, you would do 360 degrees minus 45. So if I did all the way around in radians and minus my reference angle, I'd have to get a common denominator. I could figure it out that way as well. So we're going to need to know our families and be able to quickly say all the angles in that family. But we can revert to some of our skills from the past with reference angles, like all of a sudden you forget, well, it's not hard to figure it out. So that's what I'm trying to show as well. Okay. Now, in order to get the coordinates, and if you have find some space on this front page, maybe on the, I think there might be a little bit of space in that little section right up there, one in the bottom corner. I would like you to write special triangle for 45 degrees. And in brackets, I'll write in radians, that would be pi over 4. So the coordinates on our circle are sine theta and cos theta. And if we go back to what we knew about trigonometry in the past, we figured out sine of theta was opposite over hypotenuse if you had a right angled triangle. Cos of theta was adjacent over hypotenuse if you had a right angled triangle. So the special triangle for 45 degrees, I'm going to have to draw a right angled triangle, and I'm going to have to make one of the angles 45 degrees. And then somehow I need to find the opposite over hypotenuse and adjacent over hypotenuse and opposite over adjacent. Now, as soon as we make one of those angles 45 degrees, you can use another skill that you know about triangles to figure out the only angle that's left is going to be, this is 90, and this is 45. What's the one that's left? It's also 45, because angles in a triangle always have to add up to 180 degrees. And this makes it not only a right angle triangle, but there's another special triangle when two angles are the same. Do you remember the name of that triangle? Close. Equilaterals when all the angles are the same. If two of them are the same. Give you a hint. Starts with I, rhymes with isosceles. Oh, you guys are amazing. It's an isosceles triangle, and an isosceles triangle not only has two angles that are the same, but also has two sides that are the same. If those angles are the same, then the sides are the same. And if we want to, we could make this triangle as big or small as we want. I could pick this side to be 5, and then I would know that side is also 5. I can pick any number I want. For making life easier, so our mental math is not as bad, I'm going to say this side is 1, and this side is 1. Could I figure out the hypotenuse? Yes, it's a right angle triangle. You know a squared plus b squared equals c squared. So if I pick 1 squared plus 1 squared, 2 square, this will make a squared plus b squared equals c squared. That will make that side the square root of 2. I'll tell you, if you picked 5, then it would be 5, 5, and 5 square roots of 2. If you picked 10, it would be 10, 10, and 10 square roots of 2. It'll just be the same numbers, just a multiple of each of the sides, because you're making it bigger or small. But the cool thing about this is now we did that without a calculator, just knowing that it was an isosceles triangle, and I can now write that sine of 45 degrees is opposite, which is 1, over hypotenuse, which is root 2. And do you remember in grade 11 that you weren't allowed to have square roots on the bottom? You had to rationalize the denominator, so you would have like multiplied by root 2 over root 2. And then you would get root 2 over 2. And cos of 45 degrees is going to be identical. It's also going to be root 2 over 2. You want to find out something cool about the grade 12 pre-calculus? They assume you know how to rationalize the denominator. So they will accept if you either write root 2 over 2 or 1 over root 2. They won't take off marks for leaving a square root on the bottom. But almost all their multiple choice ones are already rationalized without the square root. So you still have to. Can't like, oh, great, I can throw out that brain matter and not have to remember that. No, you still need to know how to do that. You just don't have to always write it that way. And tan of 45 degrees, well, that is opposite over adjacent, which would be 1 over 1, which is just 1. Can you see if I pick 5 and 5, I'd get 5 over 5, I'd still get 1. It doesn't matter how big or how small you make that triangle, the ratios are going to stay the same. So 1, I just picked 1 because it made our mental math easier. If you wanted to make your mental math difficult, you can choose whatever difficult numbers you like. But now, we can label our coordinates because your coordinates are always cos theta, comma sine theta. So cos of theta is root 2 over 2, and sine of theta is root 2 over 2. So now we have those coordinates on our unit circle. And if you go to quadrant 2, the reason these values are important and they stay the same is because that root 2 over 2 and root 2 over 2 is based on, and I'll just draw it temporarily here, that's that triangle, okay? Where the hypotenuse is 1, I guess the x-coordinate's root 2 over 2, the y-coordinate's root 2 over 2. If I draw that same triangle with the same reference angle over there, can you see that those triangles would be identical? The only difference is that now when I go into quadrant 2, my x-coordinate is negative. And my y-coordinate is still positive. And in quadrant 3, my x-coordinate would be negative. And my y-coordinate would also be negative, because now it's down. And in quadrant 4, my x-coordinate is positive. And my y-coordinate is negative. Now you can use your special triangle to get tan is 1, but we could also use the big idea that tan is sine divided by cos. Sine is your y-coordinate, cos is your x-coordinate. If you did root 2 over 2 divided by root 2 over 2, you would get 1. If you go to quadrant 2, tan of 3 pi over 4, you did sine divided by cos, you will get negative 1. Because now cos is negative and sine is positive. And if you go to quadrant 3, and you do sine divided by cos for tan here, you get positive 1 again. Because sine of theta was negative root 2 over 2, and cos of theta was also negative root 2 over 2. And finally, in quadrant 4, and so one thing that I find fascinating about the unit circle is it really explains why your cast rule works. Okay? Because if cos is your x-coordinate, and sine is your y-coordinate, and tan is sine divided by cos, those are the big ideas from the unit circle. Can you see in quadrant 1 that all three have to be positive? Your x-coordinate is always positive, your y-coordinate is always positive, and if you divided two positive numbers together, you would get a positive for tangent. So it explains why all of them are positive in quadrant 1. In quadrant 2, can you see if the x-coordinate is negative? The x-coordinate on your unit circle, right? Here's our big idea. Oh, sorry. The x-coordinate is negative, the x-coordinate is cos, the y-coordinate is sine. I guess, can you see that only the y-coordinate is positive? The x-coordinate is negative. What does your cast rule say? Only sine is positive in quadrant 2. Only the y-coordinate. And if tan is sine divided by cos, and you have a positive number divided by a negative number, you will get tan is negative as well. Now, both the x-coordinate and the y-coordinate are negative in quadrant 3, which is why both cos and sine are negative. But a negative divided by a negative makes tangent the only positive one in quadrant 3. And then same thing, quadrant 4, cos, the x-coordinate is the only positive one. So your cast rule is actually explained by the unit circle. All right, now we're going to do some mental math. Okay, and Hunter's going to pick our first volunteer. Don't pick them before I ask the question.
so everybody can get a little bit nervous. You're the only one that doesn't have to get nervous at this moment. My first question is, what is sine of 3 pi over 4? Who are you going to pick?
Root 2 over 2.
Root 2 over 2. So you go look for your angle, 3 pi over 4. Look at your coordinate. Sine is the y coordinate. Root 2 over 2. Okay, what is cos of 315 degrees? Bethany, you got to pick the next one here.
Again, it's root 2 over 2.
Root 2 over 2. So again, we go to 315 degrees. Cos is the x coordinate, and it's positive root 2 over 2. I'll do one more. So Braden, pick someone to do sine of 5 pi over 4. Okay.
Negative 2 root over 2.
Yes. So you go to 5 pi over 4. Sine is the y coordinate. Negative root 2 over 2. Excellent. Okay, let's go to our next family. The next family is the 30-degree family. So in the 30-degree family, all of these reference angles are all 30 degrees. So I'm going to give you a 15-second head start to label the other ones in degrees. Check how you did. Did you get 150 degrees here? 210 degrees here? And 330 degrees there. Next, in radians. 30 degrees happens to be pi over 6 radians. That means all of those reference angles in radians are pi over 6. Can you label the other measures in radians of the rest of the family? Again, I'll give you a little head start. Did you get 5 pi over 6? Right? Because you'd have to do pi minus pi over 6. And to get a common denominator with 6 pi over 6 minus 1 pi over 6 will give you 5 pi over 6. And then this one will be pi plus pi over 6 will be 7 pi over 6. And the last one, 11 pi over 6. Because if you went all the way around, that would be 2 pi, which is 12 pi over 6, minus 1 pi over 6 gives you 11 pi over 6. Now, in order to get the coordinates, we're going to need a special triangle again. Special triangle for 30 degrees. And what's cool is the special triangle for 30 degrees is also going to be the special triangle for 60 degrees. Because if I draw a right angle triangle and I label one of the angles at 30 degrees, if it has to add up to 180, the other angle has to be 60 degrees. Okay? Now this is a right angle triangle where all the angles are different, which makes all the sides different. And they have a special name for this triangle. And it's the one that most often you forget. Even if I give you a rhyme, you might not get this one. Or maybe you will. He doesn't give you the rhyme. But we'll pick a letter. What do you think you got it? It is a scalene triangle. Scalene is like the triangle, not special, but they thought, well, we don't want to make you feel bad, so we'll give you a special name anyways. And so they called it the scalene triangle, which is like everything's different on this triangle. has no special properties whatsoever. Unlike isosceles, which like two sides the same. So here we have our poor 30-degree, 60-degree, 90-degree scaling triangle. It's kind of sad because it's like, I'm not special. I know, I'm being a little bit mean to the triangle right now. But so the sad triangle was walking down the street because you know triangles can walk. And it ran into another triangle exactly like it, and like, oh, I'm scaling, and the other triangle's like, I'm scaling as well, and oh, they're both kind of sad. They're like, well, we're both sad, you want to be friends, and so they said, okay, we'll be friends, and so the other scaling triangle joined up. They're exactly the same, and something special. What do we have now with those two triangles put together? Now we made an equilateral triangle. And an equilateral triangle has all angles at 60 degrees. See, the big one has all angles at 60 degrees, which would mean all the sides are the same. And I could pick any number. I could go 5, 5, and 5, 10, 10, and 10. For the easiest math, I'm going to choose 2. You might think, well, why doesn't he choose 1? Can you see why I chose 2? What does that do on the bottom? Makes it 1 and 1. And then I can do a squared plus b squared equals c squared. 1 squared plus b squared equals 2 squared. And this side we can solve, and it's the square root of 3. And because of that, we can look at this triangle and now say, I can figure out sine of 30 degrees. Opposite over hypotenuse. I can figure out cos of 30 degrees. Adjacent over hypotenuse. And I can figure out tan of 30 degrees. Opposite over adjacent. And if you rationalize this one, you'll get root 3 over 3. And since it's also the special 60-degree one, I can figure out sine, cos, and tan for both 30 and 60 degrees, again, without a calculator. So that lets me label my points. 30 degrees, x-coordinate is cos, so I go to my cos of 30 degrees, I see it's root 3 over 2, so that means my x-coordinate is root 3 over 2. My y-coordinate is sine of 30 degrees, which is 1/2. And then once you know the first quadrant, the rest of the quadrants are easy, because they're going to be the same numbers, because they're the same height and the same distance away. Just what's going to change is what is positive and what is negative. So now my x-coordinate will be negative, my y-coordinate is still positive. Here both my x-coordinate and my y-coordinate would be negative. And finally, here my x-coordinate would be positive and my y-coordinate would be negative. Looking at my triangle, tan of pi over 6, or 30 degrees, was root 3 over 3. Technically, if you did sine divided by cos and divided your fractions, dividing fractions is like multiplying by the reciprocal, you would get the same number.
Carry on. I just keep going by saying everybody did a great job.
And in quadrant 2, it's the same number, but now it's negative. Quadrant 3, it's positive again, and quadrant 4 will be negative again. And now that we've done the 30-degree one, I think you're able to do the 60-degree one all by yourself. Okay? So, you've got your special triangle. You can start labeling. Try to do it all on your own. I'll put the answers up here so you can check. It is early dismissal. Bell's going to go any second. There it goes.
I'm still taking notes.
Are you working? Oh, you were having
I was trying to.
I saw you. You're so tired.
Okay, I'll stop.
No, you're not absolutely. You're not.
At least I would catch myself. And then, so long.
What?
I was thinking,
Bro, you probably didn't get it.
why are you saying this? This is very useful.